So we will have the midterm next Tuesday, right? So in about 4 days. And if you understand the homework questions well, if you can solve them by yourself, I think the midterm should not be a problem. The midterm will have a part where you have these calculations, and there will be a part where you might need to explain something in a sentence or so. Okay? There will be no calculators or anything in the midterm. Okay, no calculators. You will have only one pencil and an eraser that you could use occasionally. If you don't need an eraser, so it's just one pencil. If you don't make mistakes, you don't need an eraser, right? So, okay. So that's gonna be it. All right. No calculators. Any other questions? I put one example midterm on the web, so you can look at that. You close the door now. Could you come in? Yeah, close the door. Okay, so what we are going to do today is, again, something quite interesting. Everything we do is interesting, but this has something to do with Euler angles and angular rates. So I'm just going to write it down, and then we can talk about this. This is something related Euler angles versus P, Q, and R, the angular rates. Right. Because they are rates, they are angular velocities, right? They're also, we would call them angular velocities, P, Q, and R. So, I hope you remember what theta, phi, and psi are. They are the Euler angles, and they are obtained by rotating the vehicle-carried coordinate system by 3 rotations, by psi, theta, and phi in that particular order, to obtain the body fixed coordinate system, right? These are Euler angles. How about angular rates? Angular rates, I think we plotted this like that. At the CG, you have Z body, sorry. This is X body, and this is Y body. This is a body fixed coordinate system. And P, Q, and R is basically this, right? This is the angular velocity along X. This would be P. Along Y would be Q. Along Z would be R, right? These are the angular velocities around these angles. Now, if you add them up together, this is equivalent to this, right? These are at the end 3 vectors, again with the body fixed coordinate system. So if you add them up together, if you add these 3 vectors together, you get one vector that looks like this, and this is what we call the angular velocity of the aircraft with respect to someone looking from Earth, let's say, okay? So if this is your observer, the angular velocity of that aircraft with respect to someone looking from Earth, and Earth being flat and so on and so forth. But you can decompose this into P, Q, and R, so you have these angular rotations. So P would be the rotation around this. Look up here once again. It would be the rotation around the X body axis. So even if the airplane would be like this would be P, the angular velocity in the X body axis. Okay? So if it would be like this, it would be this. This would be P. This would be P, okay, along X body. All right? So that's the definition of P, Q, and R. Now, here's my question to you. Here's my question to you. Could this be possibly true? Could that be possibly true? Phi meaning that, phi dot here means d phi dt. So it's the time rate of change of the angle of phi, or theta dot would be the time rate of change in time So it is like an angular velocity now, right? These are now angular velocities. And this is the time rate of change in the yaw angle, this is in the pitch angle, and this is in the roll, right? In the roll direction. And these ones, P, Q, and R, they are the angular rates in the body fixed coordinate system. Now, question is this equality true or not? True. Well, think about it a little bit. Is it true or not? So how many people say it's true? Okay, that's a good number of people say it's true. How many people say it's false? Okay, C. True is winning if we had democracy. But it's false. You see? It's false. It's false. Now, why is it false? This is false. Why is it false? Now, try to think why it might be false. I'm sorry? I don't hear you. Radius? What? Yes, please. Do you agree with him? He says one of the rates are in the body fixed coordinate system and the other one is in the vehicle carried coordinate system. Could that be right? People say no. I see people, I don't believe him. Any other comments? Just think about it a little bit. Make an effort. I mean, by now you should know the answer if you had studied enough, but looks like you didn't. So think of it a little bit. You will have stuff like that in the midterm, so you need to understand stuff, right? You will not get away in this class by memorizing things, I guarantee you. So any other comments? Let's look at the axes. Around which axis is P a rotation at? Or Q and R? There are rotations around which axis? Which coordinate system? The body fixed coordinate system. It's written here, right? Around which coordinate system is the rotation of psi? This psi dot. Around which coordinate system? Around which direction? Let's just talk about the direction. Which direction is it rotate? What? Around which does psi dot rotate? What? Just raise your hand and tell me. Around which coordinate system or axis does psi dot rotate? Z. Which Z? Don't just say Z. Z? No. Z what? Vehicle. Z vehicle. So it is this one here. Z vehicle. So this here is a rotation, ZV. This rotation is here, right? So a positive rotation, so it would be like that. This would be psi dot, isn't it? So this is the rotation around ZV. And R is around ZB. So they cannot be equal for, just to start with. You look quite puzzled, which scares me. In the sense that next year I will have a lot of students in class and that will not be good for me. Okay, this is ZB and this is ZV. Okay? R is the rotation around this axis. This is R, around Z body. And psi dot is around ZV, isn't it? So R and psi dot are not equal for sure. You see? So when you said phi dot, psi dot, and theta dot are in the vehicle carried coordinate system, you are right for psi dot. Okay? So for one, you are right. But how about, now what is coming next? Theta dot. How about theta dot? In which direction is theta dot? Is it around xv? No, it's not around xv. Let's say this is north, and this is xv. Theta dot is not around xv. Around which coordinate, around where is theta dot a rotation at? Around the y-axis. So which one? The y vehicle carried? Why not? Y intermediate. Ah, so there's an intermediate coordinate system. Theta is rotated of the intermediate coordinate system, remember? So where did we do this? I did that somewhere. Remember this? Vehicle carried coordinate system. Rotate around z-axis. You obtain this. This is a new coordinate system now. Rotated around the z-axis. Right? And now you have a new coordinate system, and now you rotate around the y1 axis, not about the y-axis over here. Around the y1 axis, about the coordinate system that you newly have discovered, right? So y1, theta, is the rotation around the intermediate coordinate system. Right? You look very puzzled. This really scares me. What I'm trying to say is this. If this is north, this is east, and this is down, this is the vehicle carried coordinate system, okay? The first rotation is around psi, so you rotate around this, okay? So this is now the new coordinate system, x, y, and z. So the second rotation will be around this one, around y. So it is this, right? But if this is the vehicle carried coordinate system, north, east, and down, y is here. So this rotation is this, and after this rotation, the new y is here, this rotation is that. So it is not the same, it's not the same angle, the same axis. You see? So therefore, the rotation of phi is not around vehicle carried y. It is around, after the first rotation, the intermediate coordinate system, this y, it's around this y. You got it? So therefore, theta dot is certainly not around the vehicle carried coordinate system. It is around the intermediate frame that you obtain after you rotate around psi. Okay? What about phi then? Phi is the second intermediate frame that you obtain after you rotate around y by a theta. That's your new intermediate frame, and that is the axis of theta dot. Phi dot. So if you look at this like that, none of them are actually equivalent to PQ and R at all. They're somehow related, of course, but they are not the same for sure. You understand that? Okay. So they are not equal. So how are we going to equate them? How are we going to find a relation? If you think about it, this is a right-handed coordinate system. PQ and R is a right-handed coordinate system, right? Is this a right-handed coordinate system? Is it? No, it's not It's not a coordinate system. It's not a right-handed coordinate system. This is not a right-handed coordinate system. In special cases it could be, but generally it's not. Okay, so it's not a right-handed coordinate system. So, how are we going to relate them to each other? These are angular velocities, these are angular velocities. Somehow you should be able to represent this vector here. Sorry. This vector here, you could represent it in both, using both variables, let's say. But I know that they are not in this, this is not even a right-handed coordinate system, but you could represent this vector also using these variables. Okay? So I'm going to try to do that. First of all, let's write the velocity vector in the body fixed coordinate system. Okay? And for the sake of easiness, let's just make it with respect to the inertial frame, okay? Or inertial is equal to Earth or something like that. So it's this. So writing the angular velocity of this airplane, I can write this, right? P I B plus Q J B plus R K B. And note that IB, JB, and KB are unit vectors around the body, unit vectors, say not around, on the body fixed coordinate system. Okay, so IB is in body Y, body X, body Y, body Z, so P, Q, and R, they are in these directions, and they constitute this angular velocity. All right? So let's try to write the same velocity vector using a combination of theta dot, phi dot, and psi dot, putting the appropriate unit vectors, writing the appropriate unit vectors. So this is what I'm going to write. So psi dot is around what coordinate, what axis? X, I mean Z vehicle carried, right? So therefore vehicle carried K. So it is in the vehicle carried Z direction. So IJK meaning that X, Y, Z. So K would be in the Z vehicle carried unit vector. Is that good? Is psi dot in that direction? Okay, it's there, right? I mean north, east, and down. So down is in the vehicle carried coordinate system, so it is KV, the unit vector, right? So psi dot is around this vector. The second one, theta dot, is in which direction? J1, right? J1. What is 1? 1 is the intermediate coordinate system. I mean, it is this one here. Look up here. Theta is around J1, I mean Y1. So it is J1 is the unit vector, right? This one was around Z, so this was KZ, this was theta, and now we are going to phi. So it is Y1. And here you can already see where is phi is a rotation around. It is around I2 plus phi dot times I2. So theoretically, these three angular velocities along these axes, which might not be a right-handed coordinate system, these three, if you add them together, these are like three vectors, you add together and you obtain omega, the angular velocity of the aircraft. But this is not a right-handed coordinate system. This is more like adding three vectors together. You're adding these three vectors together to obtain this angular velocity vector, basically obtaining this vector here. Here, this is written in a right-handed coordinate system. That's fine. This is not a right-handed coordinate system. But you can add these three vectors, like adding any three vectors, to obtain omega. So if I can obtain the same angular velocity using these ones, I could maybe find a relation between these ones. You see what I'm trying to do? Okay. And here is how we're going to approach this. We are going to write everything on this thing in the body fixed coordinate system. Meaning this. If you look at this number, this vector, it is written in the vehicle carried coordinate system. It is a unit vector in vehicle carried z. Can I transform this vector, this unit vector, into the body fixed coordinate system? Yes. How do I do that? How do I do that? Well, we have our transformation matrix. We can transform any vector from one coordinate system to another coordinate system that we already know. So we are just going to transform this to something else, to the body fixed coordinate system. So I'm going to do this. KV, that's the vector, written in the body fixed coordinate system, will be equal to the transformation matrix from vehicle to body. Hopefully this vector I can write in this coordinate system. So this will be L3 phi, L2 theta, KV. So and that will be LBV, and since it's a unit vector, it's 0, 0, 1. Why am I not rotating around psi? Because this is already in the vehicle, it's already in psi, so I'm not needing this. But if you are not sure, you can use LBV the way we obtained it previously and make this transformation. So, do you have LBV? Can we write this down in any way? I think we wrote the matrix, right? We have the matrix somewhere. Let me try to find it. Here it is. From vehicle to body. Remember this? And this is the transformation matrix. Right? So all you need to do is look up here. 0, 0, 1. Multiplied with this, what do you get? 0, 0, 1. So when you multiply it, you just get this row, isn't it? So it will be this, this, and that. Is that okay? All right. So let me write it down then. It would be minus sine theta I plus sine phi cosine theta j plus cosine phi cosine theta k. Yes.
Why don't we transform psi dot, because that's the quantity which we are interested in.
Why are we not using psi?
Yes.
See, in this equation, I mean, I will tell you in a second, but in this equation we have psi. But it's not here, you see. So even if I was using psi, it would just give me this. And there's no psi. Do you know why there's no psi? Because the rotation of k, you don't need a second rotation, you don't need a third rotation of k around psi. Because, you know, look up here. KV is in this direction. Right? KV is here, north, east, down. Rotate around E here. This is the intermediate frame. Where is KV? Still here. So in fact, you don't need to rotate around KV because KV is already in the Z direction. If you rotate it, it's still the same vector in the Z direction. So therefore, you don't need a rotation there. But you can include it. It will just give you 1. Okay? And you can see it after we do the big matrix. You see it's not even there. Does it make sense? Yes?
KVB is a unit vector?
No, it's not a unit vector anymore. You see? It is a vector of dimension 1. Right? I mean, these two, this and this, they are the same vectors pointing in the same direction. They are now written in different coordinate systems. KV was written in the vehicle carried coordinate system in the Z direction. The direction and magnitude has not changed. Now the same vector is written in the body fixed coordinate system, which means if you add these 3 vectors, you would actually obtain this one. And these are the unit vectors in the body fixed, of course, right? I didn't write them. They are now in the body fixed coordinate system. So there are 3 vectors. If you add them together, you should still obtain a unit vector in a direction that is in the Z vehicle carried coordinate system. Does that make sense? So it is a unit vector in a sense. It's still a unit vector, but not in the body axis system anymore. The body axis system has these unit vectors. It is like this. Let's say this is the body axis system. Okay. X body, Y body, and Z body. Okay? Now you have these 3 components. You add them together. You add this plus this plus this. You add them together. You obtain this, KV. Okay? This is, the magnitude is 1, so it's a unit vector. But the direction is in none of these directions. In which direction is it? It's in the direction of ZV. In the direction of ZV, it is still a unit vector. It's still the same vector. It's just decomposed into the body axis system. That make sense? All right? Okay, so this was KV. Here's my question to the class. Now, can you write this one in the body fixed coordinate system? Let's try to do it, please, in 1 minute. Because I did it for KV, you can do it for J1. And tell me what the result is. I should be playing a music when I do that. Now, and you try to find the result. You understand your task, right? Yeah, sorry. Absolutely. You could use this. This is actually not right. You're absolutely correct. This is LB1. Okay? This is LB1 because you're going from 1 to B. Okay? But it is the same as going from vehicle to body. No, this is not good. This is just confusing. Okay? Thank you. This is very good. So you're going from the vehicle from the 1 to body, which means after 1 you need 2 rotations. One would be phi and beta, theta and phi, right? However, you already made after the first rotation nothing happens, so you only need phi. Okay. So this is the result if you are still working on it. We are trying to get the j unit vector from the intermediate coordinate system 1 and move it to body. And therefore, the transformation matrix is from the intermediate coordinate system 1 to B. Okay? From intermediate coordinate system to the body fixed coordinate system. So, okay, what does it mean? After the first rotation in psi, we are here. This is our new coordinate system, right? X, Y, and Z. All right? And we have this J. J is here. J1. Right? J is here. So we are going to make a rotation around this J1. So it's going to be like that, right? So after the first rotation, we're going to, this is J1. We first rotate around theta. It is still around this J, so it doesn't change. Therefore, I don't need a rotation around theta for that transformation. After I do this, but if I do that, I will have 1, right? So therefore, the only rotation I need is around phi. Okay? And that's what I have here. Rotation around phi in the x direction, J1, and this will turn you into body. So this is that. Let's make the third one. I'm talking about this. Talking about this one. I2. Can you transform I2 into the body fixed coordinate system? What will it be? Is equal to I2 already. Right? Because I2 is already in the intermediate x-axis, right? This is I2. So you rotate around this, it is still in the x-axis. So therefore I2 is already in the body axis system. So it is actually IB. So that is indeed IB. So then that means omega is equal to, let's write it here, let's write it nicely. Omega, therefore, is equal to phi dot IB plus, what did we have for this one? It's over here. So it will be theta dot times 0 cos phi minus sine phi. And this is now in the body axis system, right? This vector is now, it's not a nice writing, I apologize, but this is the best I can, in order to demonstrate. And this is psi dot times the LBV that we obtained times KV. Okay? So I could write it like this, phi dot IB, let me try to write it a little nicer, plus theta dot cosine phi, which is JB, plus theta dot minus sine phi k beta, right? This is the theta part, plus, where did I put the other one? Plus this one. Sorry. Right. This one here is the one that is related to, so it's basically this. This one here is related to the psi dot rotation. And this one here is rotated to the theta dot rotation. Oh, you have psi dots everywhere, of course. Psi dot, psi dot, psi dot, sorry. And this is related to the theta dot rotation. Okay? And they should be equal to, if it's the same vector, PIB plus QKB plus R, JB, I'm sorry, JB plus KB. And they should be equal to each other. Okay, they should be equal to each other. So, and now all I need to do is regroup these IBs, right? Regroup these IBs and equate them, right? For example, let's look at the IBs. How many IBs? The IB is P, right? So I equate them. I equate these two equations. So what will I get? I will get this. P, you know, IB, this is in front of IB. So what do IBs? IBs, I have here this one, phi dot. And what do I have here? Minus psi dot sine theta. You see, IB, these two, adding them together should be equal to P. Because this is the same velocity, angular velocity vector. It is equal to this one. Do the same thing for J. You will obtain Q is equal to theta dot cosine phi here, and you have one more here, plus psi dot sine phi cosine theta. Do the same thing for R. You will obtain R is equal to minus theta dot sine phi plus psi dot cosine phi cosine theta. So what do you think? Understand what I'm trying to do? So this was the angular velocity vector of the airplane along the body x-axis, IB, JB, and KB. And along these axes you have P, Q, and R, right? P is in X, Y is in blah, blah, blah. Now all we did was we took the velocities, the angular velocities that are related to theta dot, phi dot, and psi dot, and wrote them in the appropriate coordinate systems. And the appropriate coordinate systems are these. The appropriate coordinate systems is psi dot is around kV, theta is around J1, and phi dot is around I1. So what I'm claiming is, if I would rewrite these coordinates, meaning J1 and I2, in the body fixed coordinate system, if I transform them, because I know how to transform vectors, if I transform them, I obtain this. You know, everything is transformed. It looks quite long, but it's the same vector. So since this is the angular velocity vector now, I can equate this with this, because both represent the angular velocities of the airplane. And then you equate P to this, Q to that, and this R to the rest, you know, the vectors, the vector components, and you obtain this relation. Now, if you have a question, is P, Q, and R equal to theta dot, phi dot, and psi dot? The answer is no. This is how they are related to each other. Okay? This is how they are related to each other. In fact, you could write this in matrix form, and in matrix form, it would look like this. Let me write this in matrix form. It would look like this. P, Q, and R is equal to 1, 0, sine theta, 0, 0, cosine phi, sine phi, cos theta, minus sine phi, cos phi, cos theta, phi dot, theta dot, and psi dot. And this is the relation between P, Q, and R and theta dot, phi dot, and psi dot. Do you see that now? Yes, please. Could be. You mean this one?
Not this one. About 1, 0 minus sine theta.
Yeah, it's a minus. Thank you. Okay? So that's the relation. And you understand why they are not equal, right? What is the answer if I ask you in the midterm, why is PQR not equal to theta dot, phi dot, theta dot, phi dot, and psi dot? Why are they not equal? Because they are not around the same axes. One is in the body fixed coordinate system, the other one is through 3 different weird coordinate systems, right? Some rotations after rotation after rotation. So theta dot is in another direction, phi dot is another, psi dot is another. But PQR is in the body fixed coordinate system, so they can't be equal, right? And they are related to each other. If you want to have a relation, a geometric relation, this is the geometric relation. Okay? Now 2 things. First question, or first note. Note that this is not a function of psi. This is not a function of psi. It's only a function of theta and phi. That comes from the fact that k vehicle, the first rotation of the k vehicle, psi dot is already in k vehicle, right? It comes from there. So we didn't have to need another rotation for kv. We didn't need another rotation, therefore it's not a function of psi. Second question, is this a transformation matrix? Now that's a trick question. Is this a transformation matrix? No. Why not?
The transformation matrix transform one coordinate system to another.
So isn't that what we are doing here?
No.
Okay. Why not?
Because
So that's a coordinate system, P, Q, and R, body fixed coordinate system. How about this one? It is not a coordinate system. That's the answer. These axes don't complete a right-handed coordinate system. They are in different directions in 3 different coordinate systems. It might so happen that they might become a right-handed coordinate system in a very special situation. But generally, they are not a coordinate system. They are not along a right-handed coordinate system. Therefore, because this is not even a coordinate system here, this cannot be a transformation matrix. Understand? Okay, if it's not a transformation matrix, I would like to know what this would look like. Do you think the transpose of this is also the inverse of this, like in a transformation matrix? Coming back here, now I reverse the directions. And now, of course, you need to take the inverse. But in the transformation matrix, it was really nice because you could only take the transform of this. Is this still applicable here? Can I take the transform and put it here? No, because this is not a transformation matrix. The inverse of this is not the transpose of that matrix. In fact, let me write it down. Let me write you down and show you what it actually looks like. It looks like this, 1, 0, 0. If you take the inverse of this matrix, it is sine phi tangent theta cosine phi tangent theta cosine phi minus sine phi secant theta cosine phi secant theta. So this is the inverse. So if I would call this r theta in phi, this one I would call r inverse theta phi. Okay? So this is the inverse. And since the inverse is not a transpose, we can see immediately this is not a transformation matrix. So what is it? It is just a matrix, it is a relation. It's a relation between these numbers and these numbers. And that's so that you always get reminded that it's only a relation. I put an R. Okay? So when you see this R, you know it's a relation. Okay? It is relating these numbers to these numbers. It is not a transformation matrix. We are not transforming a vector from one place to another. It is a relation between these numbers. Okay? Any questions? Okay, so let's give a break and think about it a little bit, okay?